Hi there, this is Martin. I'm here to show you my most recently implemented machine learning model. It's a deep learning model that helps you transcribing handwritten text into searchable text. Let me show you. I type in "Hi there," and upon clicking the button predict, the model is used in inference and you can see the prediction text to be correct. This video here comes together with the corresponding GitHub code and will consist of 3 parts. In the first one, I will show you the paper that I re-implemented in order to obtain the model. It's a paper by Victor Carbune from 2020 and is called Fast Multi-Language LSTM-based Online Handwriting Recognition. The second part shows my implementation, and then the last part shows you how to use the model yourself. The paper that I re-implemented and all the code that I'm showing you and the results are based on that re-implementation of the paper. Fast multi-language LSTM-based online hand recognition. There are really 2 approaches to handwriting recognition. The first one is the so-called offline approach, which uses images. For example, you can see here, "Hi there" written out, and a computer vision based model would take it in and predict the words "hi there." An alternative approach is the so-called online approach that uses the dynamics of the underlying pen, denoted by red dots, which are points at coordinates x and y given at time t. The work here is exclusively using an online approach, so that requires the system to have access to the underlying data of the handwritten strokes. The model that I implement, as I said, is based on the Carbune2020 et al. Paper, and it's a deep learning based system. It takes an input, a stack of bidirectional recurrent layers, and then finishes off with a softmax. The input is based on the strokes, which again consist of x, y, time, and number of stroke data points, while here it has to be said that the paper goes into a number of possible representations based on that knife implementation. My implementation here is solely based on x, y, t, and n. Then a stack of bidirectional LSTM layers follows and everything is wrapped up with a softmax. The loss function is a so-called CTC loss, which takes care that the labels which are predicted and the labels that are the ground truth are aligned properly. My model implementation really uses 2 underlying parts. The first one is PyTorch Lightning, which deals with all the training and the model implementation, which is essentially a layer on top of PyTorch. And the other part is Hydra, which is a configuration framework that allows flexible configuration of the system. Okay, let's go over to the code, where I will not only show you the code on GitHub, but also how to install it. Okay, so here you can see now the code. The very first entry point really is the README, where I again reiterate a bit about the motivation and the underlying technology used in that implementation here. I show you the demo that you've seen previously, and I link to this video for people to make it understandable. The more interesting bit now for you is probably on how to install it, and everything is centered around Conda environments for that. So you follow these 5 steps, and then you have the project installed completely, which essentially consists of first creating the environment, then installing everything with respect to the requirements, and last but not least also installing the project itself. Training from scratch can then be performed by calling the train script, which is called by bash scripts. Now off to the last bit of this short video here, which is the presentation of the code, so that you can get started within maybe a few minutes, hopefully. So first of all, the project is installable by using a setup.py function, which is again used in the installation procedure. There is a test framework implemented in the tests using PyTest. I implemented a couple of tests for all the data structures in code that I wrote, which you can see here. Then the main code really lives in the source subfolder. The top level files here are all scripts that you can call for training, for evaluation, for drawing a sample that you can then store, but also drawing a sample that you can then run inference on, as I've just shown you. And then the underlying modules are structured in data, models, and utilities. Okay, the script subfolder are the so-called start scripts. So within these scripts, the train script is called. It's essentially just a way for people, mostly me, to remember how to start a training. Notebooks goes into a number of smaller details. Logs and data are the resulting output files and the data files that are ingested, everything here is trained on the IAM online database. Documents consist of mostly the project website, and last but not least, the configs folder serves as the config folder for Hydra. So all the training scripts access this folder in order to be configured. And with that, I would like to end the quick project demo, and I hope you have fun. If you would like to contribute back, please do so. I appreciate any help in improving the project even further, because I have not implemented all the features that Victor Carbune did in his paper. If you like the work, I would also appreciate a GitHub star, obviously. Bye bye.